Great. Thanks everyone for joining. Today we are glad to have Yuda talking about to distill or decide. Yuda is a fourth-year PhD candidate at Carnegie Mellon University, advised by Artie Sieg and Drew Baniel. His research focuses on the theory of interactive decision-making, and he puts emphasis on efficient and robust learning in reinforcement learning with application to LLMs and robotics. Today he's talking about this question to distill or decide. Thanks a lot for accepting our invitation, and the stage is yours. Thank you again.
All right, thank you, Luca. Hi everyone. I'm Yuda, and today I'll be talking about the algorithmic trade-off between two dominant approach for learning under partial observability. One is privileged expert distillation, which is Distill, and the other one is standard reinforcement learning, which is Decide. And this is joint work with amazing collaborator Drew Rohati and Artie Singh and Drew Bagnell. So to set up the stage, some of the most impactful application of reinforcement learning nowadays involve agent that needs to operate from high-dimensional sensory input, especially images. And on the left, we have a humanoid robot trying to learn to walk and balance using vision. And on the right, we have autonomous driving, where the vehicle needs to make a real-time decision based on camera and sensory and data input. And this creates a real challenge for learning because the agent has to simultaneously figure out how to interpret these rich inputs and how to act well based on them. And these two problems, learning to see and learning to act, are deeply entangled, and this entanglement makes training sometimes significantly harder and less stable. So there is a natural question here is, can we somehow separate these two challenges? So there is a key structure insight about these domains. Behind all of these high-dimensional sensory data, there is a compact, low-dimensional latent state that actually governs the dynamics. For autonomous driving, that will be things like GPS coordinates, speed, or heading. Or for a robot, it will just be joint angles and velocities and locations. And if we knew the existence of such deterministic mapping from observation to latent state, we will get a perfect disentanglement between these two challenges that are normally tangled together. One is, again, learning to see, that is extracting the relevant state from raw perception, and the other is learning to act. Again, figure out what to do given the state. So then we can just solve each of the component independently, which is much easier to solve them jointly. But the challenge is, can we always get this perfect disentanglement? And the answer, unfortunately, is no, because such deterministic mapping doesn't always exist because of partial observability. Because the latent state may not always be uniquely determined, even if I gave you a history of observations. And there are several concrete reasons for this. For example, you might be missing the entire sensory modality. For instance, a robot might have vision input, but has no tactile sensing. That will always result in failures such as the video shows. And there's a collisions. And on the right, you can see a driving scenario where a child might appear from behind a parked car that you can never see, or you don't know exactly when a red light will change. So these are the aspects of the true latent state of the world that simply cannot be visible in the observations. So how is this rich observation and partial observability addressed in practice? I guess the most straightforward way is to train with end-to-end RL and get policy that operates on long history of observations, but this is apparently expensive. And the second approach, which is getting increasingly dominant, it is expert distillation, which is also called teacher-student learning or learning by cheating. And the idea is, for example, start with in simulation, you will have the access to the true latent state. So you will first train a privileged expert that gets to cheat and see the state directly. And then you can distill that expert into an observation-based student policy using imitation learning. And you can also get this expert demonstration through teleoperation. That is a human controlling the robot directly. That is shown on the image on the right. And the key appeal of this expert distillation approach is that it achieves exactly the disentanglement that we talked about earlier. Because think about in the sim to real setting, the RL phase that you train the expert in the latent state handles learning to act on the clean latent state, and the imitation phrase handles the part of learning to see, because you are learning the mapping from observation to the right behavior directly. So one thing you might wonder is, why is this teleoperation is still a privileged expert, even though you see on the image that the human is wearing a headset? So you can see in the video that the red block corresponds to the actual input of the robot, but the human operator is still able to put the ball in the basket, even though it has been out of sight for the robot for this whole time. So in this case, the human is still leveraging privileged information. For example, their own depth perception, spatial memory, peripheral vision, and that goes well beyond what the robot camera captures. So, nevertheless, expert distillation has resulted in many remarkable applications of sim-to-real robot applications, and this teleoperation data collection has become the dominant approach nowadays for general purpose robotics policy pre-training. And theoretically, previously people has also shown that expert distillation is probably more efficient than end-to-end RL in the setting without partial observability. But things are more nuanced in the partial observable setting. So this brings us to the central question of our work. What is the algorithmic trade-off between these approaches in a more realistic setting? Okay, here will be a roadmap for the talk. And in the part one, I will give an overview of the main result, both the theoretical framework and the empirical findings. And then in part two, I will dive into some of the details of the theoretical analysis. Okay, let's start with part one, the overview. So here is the high-level picture. Okay, we can show that the suboptimality of both expert distillation and RL can be characterized by two types of errors. And the first is the belief contraction error. And this measures how much information you will lose by using only a recent window of frames instead of the full history. And you see both RL and distillation are affected by this error. And the second is the decodability error. And this measures how non-concentrated the true belief state is. And for those who are not familiar, I will define this belief what belief state means, but just think of like belief state as your estimate of the true latent state given the observation. Okay. But this decodability error is measured on the true belief state, which is defined over the full history. Okay. Intuitively, if the belief is spread out, then the latent state is generally ambiguous from the observations. And this is the problem specific for distillation because it's trying to mimic a policy that sees the true state. And again, intuitively, these terms will become zero if there is no partial observation. And one can understand this term as a misspecification to the true latent expert due to partial observability. And now, when are these errors well behaved? We will study this under what we call the benign observability, specifically our proposed model called the perturbed block MDP models, where observations are informative most of the time. And for audience who are familiar, just think of settings such as gamma observable POMDP, for example. So under this perturbed block MDP model, we can show that belief contraction error is controllable. It will decay exponentially as you increase the frame stack length. So for both RL and distillation, using more frame stack helps with this component. And since RL only requires the belief contraction error to be small, then we can immediately obtain the guarantee of RL under such benign observability, suggesting that RL should generally works in practice. Okay, but the decodability error tells a slightly different story. Its behavior will be determined by the latent dynamics, specifically whether the dynamics are deterministic or stochastic. And this is the key divergence between the distillation and reinforcement learning. So specifically, when the latent dynamics are deterministic, decodability error is also controllable. And it's quite intuitive because deterministic transitions don't really spread out the belief. So each observation will concentrate it further. So the belief becomes increasingly peaked, and distillation works well in this setting as well. But when the dynamics are stochastic, the decodability error becomes irreducible. And because, again, intuitively, stochastic transitions will spread out the belief at each time step. And in the worst case, no amount of frame stacking can recover that in the worst case. That means expert distillation fixes a fundamental error that RL does not. Okay. So this is exactly what we see experimentally. I do not prepare many information for the setup of the experiment, so like feel free to just jump up and ask about the setting. But here we are looking at the dog walk and humanoid walk shown on top right from DeepMind Control Suite. This is a task where you do have visual input, the images, and you need to output actions to control the locomotion of the robot. Okay, but in this setting, we had deterministic latent dynamics, and we compare behavior cloning, which is the offline distillation, and Dagger, which is online distillation, and the standard reinforcement learning. And on the x-axis is plot against the wall clock time, and y-axis is the cumulative reward. And online distillation with Dagger achieves the best performance and converge faster than RL on both tasks. And offline distillation with behavior cloning, it is somewhat okay on humanoid, but does not really work on the dog environment. But the takeaway is, with proper algorithmic choice, specifically online distillation, the expert distillation approach can be more efficient than RL when observability is high and latent dynamics are deterministic. So what about the setting with yeah, so it's actually also so the question from actually is RL sensitive to specific RL algorithm? The answer is yes. So actually making any RL algorithm work end to end in this like high dimensional locomotion control is quite challenging, especially for a humanoid. And there were like a very long history of efforts on this in the deep RL community. And this is like at the time of paper writing, luckily there is finally some algorithm that works on basically all these image-based locomotion control called Mr. Q. And so we basically adopt this one for we basically adopt this one algorithm for all of these method. But yeah, to some extent, it does for the RL. It does depend on the algorithm. But okay, Arish asked why does RL has more noise than say expert distillation? Well, I think for dog, like
No, I think he's saying the online distillation seems to have less noise than RL and BC, right?
Oh, yeah, I was just curious. Like, it seems the bands are narrower. So, is there any understanding for why online distillation is so much more robust?
So these bands are just completely different independent rounds.
Sorry, which band?
No, I mean just generally the error bars, like the
error. Yeah,
or no, like basically, I guess maybe it's up and down. Like, is it just a?
Oh, you mean the oscillation in general?
Yeah.
It's okay. We can also display. I was just curious, like, why the wiggliness seems lesser in like distillation as compared to RL.
Yeah, I think whenever distillation works, it is more stable than RL. Because again, like the intuition is whenever you jointly train things, it like because like when you do online distillation, at least the latent expert is already fixed, right? So, but things are generally more unstable in the if you train things into it.
Cool, thanks.
Yeah. Yeah. So in the stochastic setting, the way that we model the stochastic environment is to inject motor noise into the latent dynamics. And it is with a standard error 0.2 for humanoid and 0.3 for dog. And then the conclusion kind of flips because in this case, RL with enough frame stacks, which is shown in red, performs generally better than Dagger in asymptotic sense. And Dagger is shown in blue. And higher intensity of the color denotes more number of frame stacks. And we see in general, both methods benefit from more frame stacks. And the more important message from this experiment is, and as the theory suggests, that under stochastic latent dynamics, RL eventually will outperform expert distillation, but with higher computation cost. And before we go into the theory, I want to also preview intervention for addressing the failure of expert distillation under stochastic setting. And the key insight is the optimal latent expert is not always the best expert policy to distill. Here, we train latent expert under different level of motor noise from like standard deviation ranging from 0.1 to 0.5, and distill each one with stagger into the environment with noise level 0.2. So this is the regular expert, which is trained at the same level, noise level 0.2. And you see, it does not result in the best student policy. However, expert trained with higher noise achieved well-result students with higher performance. And the intuition is they are smoother, so they will play similar actions for nearby states, which makes them easier to imitate under partial observability.
Anyway, so what are you? What
Yes.
is the noise being injected? So you have an expert that takes an action based on some latent state, right?
Yes.
So are you just take the real latent state, perturb it, and then feed it into the expert policy? That's what you're doing?
So the motor noise is constructed by the whatever a policy takes an action, it will inject a Gaussian noise to the action that the policy output.
Oh, it's not perturbing the state; it's just
No.
perturbing the action itself.
Yes.
Oh.
So we gave a small example in the paper on why these, like, even if you just inject noise,
Oh, yeah, I don't understand them, but I mean, asymptotically, wouldn't that not really play any role? Because I mean, if I don't know what's is this continuous? This is a continuous action domain, right?
Yeah.
And when you do BC, you're doing regression, I assume.
Yes.
But then if you just add a label noise, then wouldn't that be basically denoised asymptotically when you have infinite data?
I think
because when you do regression, you're just learning the conditional expectation, right?
true.
So I mean, so I guess it will have a transient effect, but I don't see why.
I think the difference here is, like, in practice, the noise is actually not asymmetrical because it's a truncated Gaussian. Like the actions will be truncated to between 1 and -1 in practice. It's not like symmetric Gaussian in practice.
Okay.
Yeah.
Okay.
Yeah. Otherwise, I agree.
I guess Luke has a question.
Yeah, I had another question. If you can go at the slide before,
Mm.
I was wondering which was the performance of the expert for doing distillation.
For this case.
Yes.
So the expert is
Or what is the expert in this case? Is it an RL policy?
yeah, it's the same. Like, you train the RL policy under the like latent MDP. And the expert policy, if I can recall correctly, is around like 800 cumulative return.
I see. Okay, very interesting.
Yeah. So like the adding small amount of noise doesn't really make the latent expert performs that worse. In like, okay, to give a sense, the maximum amount of cumulative reward you can achieve is 1,000.
Okay.
Yeah.
Okay.
Yeah. Yeah. So the smooth expert actually provide better student, and I will talk about why this is the case later. Okay. So if we don't have any further question, I will move on to the part 2 about giving more details on the theoretical side. Okay. So let me set up the formulation. And we will work with a finite horizon layered PUMDP. We will have just standard notation observation space X, latent S, and action space A, along with the latent transition dynamics P, and emission distribution O that maps latent state to distribution of observations. And given a time step H and a window length L, we can look at a window of the most L-step recent history, and we will denote this history space with superscript on the X, and we will also denote the history of action or latent state similarly. And one of the key concepts is this L-step executable policy. That is the policy that we will use in practice that maps the last L-step observations and actions to the distribution of the next actions. And this is what the agent actually uses at test time because it only sees the observations but not the latent state. So a trajectory is generated by sampling states from the latent dynamics, observations from the emission, actions from the policy. And the PUMDP also defines an underlying MDP, where the state is fully observable. And a latent policy is a policy that maps states directly to action. And this is what we call the privileged policy that we talked about before, and the one that gets to cheat by seeing the true latent state. And it will also define an upper bound on the performance on what we can hope for, because the optimal latent policy is always at least as good as the optimal executable policy. And for notation simplicity, we'll just use this pi latent to denote the optimal latent policy from now on. Okay. And also, as I promised before, for those who are familiar, you can skip this part, but the belief state is the posterior distribution over the latent state given the observation history. And it is recursive defined by the base rule as we get more new observation actions. And this is the detailed update operator, which first propagates the belief forward with the transition dynamics P and apply base rule with the new operations. But don't worry about it if you're not familiar, but just think of this as like an estimate over the distribution of the latent state given the observations. Okay. And after we have this, we can have the key construction for which is we call the composed policy. So given a belief distribution B and the latent expert pi latent, the composed policy is a policy that marginalizes over states. So it weights the expert action by the belief probability of each state. Okay. So if the belief is a delta distribution, then this will recover the latent expert's action. Okay. So this is all these notations to set up this like more formally for expert distillation. Okay. So we will have a latent expert. And again, think of this as an optimal policy in the latent MDP and training distribution. And the objective is to find an L-step executable policy that best predicts the expert's action distribution given the observations. So with behavior cloning, the data comes from the expert's own distribution. And with stagger or forward is just non-stationary version of stagger. A comes from the learner's distribution. So, and just think of the loss L, something like KL. And so then in the infinite sample regime, we can show that forward methods like forward will recover exactly the composed policy, which is the latent expert apply to the approximate belief under the L-step history. So this motivates us to study the performance of such composed policy instead, which is again a approximate belief with the optimal latent policy. So here's the key lemma. We can bound the suboptimality of any composed policy. I leave the definition on the top right corner. By the performance difference between the composed policy and the optimal latent policy, because again, the optimal latent policy achieves higher returns than the optimal POM-DP policy, which is again bounded by the TV distance between the visitation distribution and optimal policies, optimal latent policies trajectory distribution. By the trajectory visitation distribution between the optimal latent policy and the composed policy, because the trajectory reward are bounded. And finally, it can be bounded by the two terms that we already saw in the overview, summed over the time step. And the first is the decodability error, again, how uncertain the belief is about the true state. And second is the error using only most L-step recent frame instead of the full history. And precisely, the decodability error measures how non-concentrated the true belief is, specifically like 1 minus the max probability under the belief. And when it is 0, the state is fully determined in a non-partial observable setting. Okay, and the belief contraction error measures the distance between the true belief, which conditions on the full history, and the approximate belief using only L-step recent frame with a uniform prior. So one small detail is the belief contraction error used in the bound above is slightly different in the sense that it is not defined over the uniform prior, but they are directly comparable in the settings that we'll discuss later. Okay. So
yeah, well, I mean, yeah, I think actually was asking how is the approximate belief defined, and you introduced this uniform. This is I have a related question. It's a little nitpick. Isn't the uniform here like quite arbitrary? So I mean, just
yeah, it's like
well, we have something related because so we have this off policy OPE in POM-DP paper where we also need to define some kind of like similar quantities here. And I think our first version used uniform and the results were fine, but there were some artifacts, but then they figured that you probably want to define it as, for example, the latent distribution under pi or something.
Yeah. That's the second one. Yes.
Oh, okay.
Yeah.
I see.
Yeah. I think like it's for historical reason, right? Like Noah, those guys, like their algorithm is trying to get uniform cover, like the coverage policy cover, right, for the latent state. So I think this is how they, I actually.
Hey, can I ask a question?
Yes.
So you mentioned that somehow only forward has this guarantee that it converges asymptotically to this latent composed with approximate belief.
Yeah.
Is this because of your definition of approximate belief? Like approximate belief is on policy?
Actually, we are not sure. Great question, because we try to prove that BC actually doesn't give you something similar.
Yeah.
And we actually didn't find a counterexample.
Okay.
Yeah. So.
But like, okay, in this last whatever epsilon, the approximate belief is measured on policy with yourself, right? Like you imagine the first H minus L minus 1 steps are taken according to me. And
Yes.
this is you.
Yes.
Okay.
Yeah, but like, ideal case, you can say that like it can also be defined on the optimal trajectory, right? If you DC did really, really well, then
yeah. Thanks.
Yeah. Mm-hmm. But importantly, in this seminal work by Noah, Anker, and Dhruv, they actually introduced the notion of belief contraction error, the first one, and they show that RL has polynomial dependency only on the belief contraction error, but under this like gamma observable model, but the algorithm requires a quasi-poly running time, right? So, but overall, the idea of this lemma is the proof is just to introduce a new comparator policy, which is the compose policy that use latent expert and true belief, right? And then you can kind of see where these two errors coming from by compare these three policies separately. Okay. So how do these errors behave in a more practical relevant setting? So to study this, we introduced the perturbed block MDP model. So the practical intuition is that most of the time, observations are highly informative, such as like a block MDP where you can read off the states from the observation, but with small probability, the observation could be somewhat arbitrary. So this captures scenarios like periodic occlusion. And formally, it's just the definition is it's a block MDP model, but the emission is a mixture. So with probability 1 minus delta, it follows the block structure, which says the observation has disjoint support per state. And with probability delta, it will be arbitrary. Okay. So now we can go back to this like full picture overview. So we show that under the perturbed block MDP model, belief contraction error decays exponentially with frame stack. So intuitively, this is with our definition is because each informative observation will contract the belief state by an order of delta per frame. So I should also mention that the prior result from Golovich et al. Also applies to this model, since any delta perturbed block MDP model is a 1/2 delta observable pump DP, I think. But their contraction rate is only something like 1 minus 1 over a very large constant per frame. So it is big unless like number of frames that you use L is at least order log S. So that's why where the quasi-poly comes from. Even when delta is very, very small. But to some extent, our result is tighter because, for example, when delta is like 1 over S, we can get small belief contraction error with only 0.1 frames. Okay. So the proof idea is like we need an error metric that is a product of the TV distance and the density ratio. So the intuition is basically you can argue that when TV fails to contract, the density ratio will shrink instead. So the product you can always track the progress made by this product term. Okay. And for the decodability error, again, it depends on the dynamics, but if you have deterministic transitions, the key is that deterministic transition cannot spread out the belief. So the model state just maps to some specific next state, preserving the max probability that we care about, because that's how decodability error is defined. So each observation can only contract the belief even further. So we'll also get an exponential decay with the time step. Okay. So these two results are somewhat intuitive, and I will give you more information on the negative result on the stochastic setting next. Okay. So I'll formulate the lower bound says there exists a perturbed block MDP with stochastic latent dynamics such that for any frame stack length L, the best L step executable policy will still has a total variation distance to the pi latent, at least in the order of delta times h. So this is a irreducible misspecification, because it doesn't matter how many frame stacks that you use, you cannot close this gap with expert distillation. So let me quickly walk through the construction. It's quite simple. So we have two states, two observations, and two actions. They are all binary. And the observation channel is just a noisy identity. So you can see the true state with probability 1 minus delta, and the wrong state with probability delta. And you can immediately see why this is like a perturbed block MDP model. And the initial state is drawn uniformly at random, and at each subsequent step, the state is redrawn uniformly, independent of the previous state action. So the dynamics is stochastic and uniformly mixing, and same for all time steps. And the reward at each step is 1 over h if the action matches the state and 0 otherwise. So the way that we prove the lower bound is you can see that the optimal latent state simply plays AH equals to SH always. And but for any executable policy, at any time step h, the current state SH is independent of all prior history, because again, the dynamics is uniformly mixing. So the only information about SH comes from XH, which is correct with probability at most 1 minus delta. Again, that means at each step, any executable policy matches the state with probability 1 minus delta. So the probability of matching the entire latent expert trajectory is at most 1 minus delta to the h. So some algebra then gives you the final bound. But this problem is trivially easy for RL because it decomposes into h independent one-step bandit problem. Okay. So one thing is that the previous slide established a bond between the Distill policy and the latent expert trajectory distribution, but I guess sometimes it is a result that's saying, okay, imitating the latent expert is really, really hard in that case, but what if we want to compare with the optimal POM-DP policy, i.e. the best executable policy? So the optimal executable policy, which RL will learn trivially, is simply place AH equals to SH. So just copy the observation. However, the Distill policy, on the other hand, tries to mimic the latent expert through the belief, right? So given observation XH, the belief put mass 1 minus delta on XH and delta on the other state. So the composed policy plays AH equals to XH with probability 1 minus delta, and the wrong action with probability delta. So the per step suboptimality compared to the optimal executable policy is the trajectory. The overall suboptimality, you can show that it's on the order of delta. And so you can still show that it is suboptimal and the error is irreducible. But you can also change the construction a little bit by adding an observable failure state. That is like if the policy, we will transit to a observing state if the policy makes one single mistake, then you can massage it a little bit and I think get the order of delta times h suboptimality compared to the optimal executable policy. So distillation can be fundamentally worse than RL under the stochastic dynamics setting. Okay. Oh.
Can I ask a question?
Yes.
Okay, maybe you've noticed this, but like in this setting, if you take this expert distilled policy and you do greedy decoding, then you actually recover the optimal executable policy.
Yes.
Uh,
So yeah, there is like at the beginning of the project, we were kind of thinking about something else. Like there was some like very old algorithm called like QMDP, I think from Drew as well, and that like QMDP will be good in this setting because QMDP is basically what you described. I distill a Q function for the MDP and I act greedily with respect to it.
I see.
Yeah, then you recover in this case, yeah.
Is there a sense that that's true more generally or just for this? Like,
no, I think it has its own failure case or lower bound. Yeah.
Okay, cool. Yeah. Thanks.
Yeah. But one thing about the construction is like it's pretty didactic, right? It uses maximally mixing dynamics, which is mostly unrealistic. And also the lower bound only gives a very abstract statement because it just tells us distillation can have irreducible error under stochastic dynamics. But like more ideally, we want to have a sense of like how the gap between RL and distillation scales if you have somewhat a notion of like increasing level of stochasticity, right? So we only did this for the experiment. So this is, again, the dog walk task with motor noise, increasing from 0.2 to 0.3 to 0.4 across the three plots. And dagger, showing in blue, stay roughly flat regardless of the frame stack length. And RL, in this case, as the noise level increases, it has an increased gap or advantage over the expert distillation. See, because you see, like at noise level 0.2, these two approaches, you can even say they are somewhat comparable to each other, but as the noise level increases to 0.4, RL with long enough frame stack can have like even twice the cumulative reward as expert distillation. So there is a kind of a progressive degradation of expert distillation relative to RL as the stochasticity increases. And but even though the theory only captures the extreme case. So I think it will be interesting to figure out how exactly to capture this kind of observation. Okay. So the final part is how to explain the intervention I just described in the first section. So if we look at this error decomposition, sometimes the decodability error can be actually loose because it doesn't really account for the property of the expert. So we can actually directly replace the decodability error in the above the bound with this action prediction error, which measures how concentrated the expert action distribution is under the belief, rather than how concentrated the belief itself is. So for a deterministic expert, in general, we will have that the action prediction error is at most the decodability error, but it can be much smaller. So this basically motivates the notion of the smooth expert. And that's the result I showed you before. So one thing to verify is this, like, okay, does this action prediction error actually get smaller as, or another question to ask is like, is the performance and this action prediction error actually correlated? So one thing we see, for example, on the humanoid task is like, recall like the ground truth noise level is 0.2, and the expert trained at noise level 0.3 or 0.4 substantially outperforms the regular expert. And you see like they do have smaller action prediction error. Although like the thing doesn't really perfectly match is like the expert with 0.5 level noise 0.5 has higher action prediction error, but still is better than the original expert. But another thing that we saw is, okay, what if you do similar things in a deterministic setting, right? So the last plot I show is like, you don't really see anything different if you try to add noise when you train the privileged expert, and the resulting student performance are roughly comparable to each other. So this, again, is somewhat consistent with overall our theory. Okay, that's basically the last result, and I think we are also kind of running out of time. But just to wrap up, so there are three, I guess, contributions of the paper, and on the tool side, there's like two areas of notions that we think we should look at in the POM-DP setting: decodability error and belief contraction error. And another thing is this new theoretical model, the perturbed block MDP model, which led us to study these errors in a kind of a practically motivated setting. And then for the trade-off, we have that RL's min cost is computationally, but because it requires longer frames and training everything end to end, but it depends, its suboptimality only depends on belief contraction. And expert distillation is faster and stable more stable when it works, but it has a fundamental pitfall under stochastic latent dynamics. And in that case, the decodability error becomes irreducible and compound with the horizon. And for the intervention side, we show that the decodability error can be tightened. The error decomposition can be tightened using action prediction error, which accounts for the smoothness of the expert. So this motivates a simple practical fix, trains the latent expert under higher motor noise to produce a smoother policy, which leads to better distillation in practice. However, this is kind of overfitting to our motor noise injection setting for the experiment. So like in general setting, we don't really know how to like model the, for example, you don't really know where the stochasticity of the environment comes from. Then like training a smoother expert is less obvious in that case. And like how to train a smoother expert is less obvious. And finally, I want to thank my amazing collaborator, Drew, again, and my advisor, RT and Drew. And thank you for attending and all the amazing questions.
Great. Thanks for the
Nice.
amazing talk.
Thanks.
Okay, thank you.
Any questions?
I think Audrey has a question.
Or she wanted to clap? Ah,
Oh, okay. I see.
yes, indeed.
Thank you, Audrey. Thank you.
Maybe I have a question concerning the lower bound for distillation. I mean, my doubt is having a lower bound on the total variation
Mhm.
does not really prevent you to learn a policy with good performance. You might have two policies that are different but achieve same reward.
Right.
Could you twist your construction to lower bound the suboptimality as well, not only the total
Oh,
variation?
yeah. After the total variation lower bound, we do show that even if you compare with the optimal policy in POMDP, it still has a irreducible error. So
Okay, I see.
yeah.
Okay.
But the thing we want, the conceptual message we want to deliver with the lower bound is it's very, very hard to imitate a latent expert in that setting.
Mhm. Okay.
I think that's
Maybe I'm gonna stop the recording
Yeah.
in case no one wants to ask out of camera.